causal inference in statistics right here. And we are on question, actually we are on example 4.5.1. And this is going to be rather lengthy, and so you may need to watch it a couple of times. But you know, so we go from from here all the way down to here. All right. So here's the basic prompt here, and I think that I will read this verbatim. So a lawsuit is filed against the manufacturer of drug X, charging that the drug is likely to have caused the death of Mr. A, who took it to relieve back pains. The manufacturer claims that experimental data on patients with back pains show conclusively that drug X has only minor effects on death rates. So again, the manufacturer is claiming that the drug has negligible effects on death rates, and just we'll come back to read the rest of the question. But if we go down here to the experimental data, these are, you know, where Y is death and X is the drug, then we see that these are the death rates. And it takes a little bit of deduction, but I believe that X prime represents taking the drug, and X means not taking the drug. But you can see that they're almost identical, and if anything, it looks like taking the drug reduces death rates. Now, the way that it's worded, I'm actually already a little bit confused because the way it's worded makes it sound like, yeah, the drug increases death rates, but it's negligible. And so then I would think that X would be taking the drug and X prime would not. But as we move forward, it's not a big deal. You know, well, this will all come out in the wash. You know, we'll figure out what all this means here. Okay. Okay, back to the question. However, the plaintiff argues that the experimental study is of little relevance in this case because it represents average effects of patients that participated in the study, not patients like Mr. A, who did not participate in the study. Okay? So in particular, the plaintiff is arguing that Mr. A is unique because he used the drug of his own volition, right? He was not randomized to take the drug, or was not prescribed the drug, I guess. Unlike subjects in the experimental study who took the drug to comply with experimental protocols. Okay. To support this argument, the plaintiff furnishes non-experimental data on patients who, like Mr. A, chose the drug to take back pain, were not a part of an experiment, and experienced higher death rates than those who did not take the drug. Okay, so that's observational data, and that is represented here. So the overall probability of death is given here. The probability of taking the drug and death is given here. The probability of death having, well, see, so already this feels a little bit confusing. I think that we're saying that X means not taking the drug, and the probability of death not taking the drug is, you know, less than 1%, and then the probability of death taking the drug is about 2.8%. Okay. So there we have, again, experimental and observational data. Okay, so now the court must decide, based on both experimental and non-experimental studies, whether it is more probable than not that drug X was in fact the cause of Mr. A's death. Okay. To illustrate the usefulness of the bounds in equation 4.30, consider the hypothetical data associated with the two studies shown in table 4.5, which you know, we have right here. We will come to equation 4.30, but this is on page 117 in your book, and it's basically just setting the upper and lower bounds of the probability of necessity, and we'll get there. All right. So now let's start trying to tackle this question. Okay, so the question is asking about the probability of necessity. And so if you remember from earlier, the probability of necessity is roughly, or I mean, it is precisely this right here. It is the probability, let me put it in terms of this example. It is the probability that Mr. A does not die, okay, if he had not taken the drug. So now I see that I may have, I am transposing the X and X prime. I apologize for the confusion here. but x prime here just represents any hypothetical intervention. And so I'm signifying the counterfactual case by putting a prime on there and then saying what it equals here. Okay, so I hope that's not too confusing. Okay, so let me start over. So it's the probability that Mr. A does not die given the counterfactual intervention where he does not take the drug, given that we actually observed that he took the drug and did in fact die. Okay, that's what we're trying to estimate here. All right. So I want to start by generating a DAG just to kind of get my head around, you know, all the moving parts here. So we have a drug and it has some effect on death, and then presumably there is also, you know, somebody's background health status that is going to have an effect on death and may affect somebody's decision to take a drug. Okay. Now, presumably in the experimental study, so the first thing to notice about this is that the effect of the drug on death is confounded by health here. And so in the study, they would have randomized who received the drug, and that would have blocked this backdoor path to get a direct effect of the drug on death. Okay. Now, if we don't have randomization at our disposal, we would have to condition on health on Z to also get an unconfounded effect of drug on death. So I take the question to be saying that Mr. A's lawyer is arguing that the drug company was negligent because they made the drug available to somebody like Mr. A for whom there is not experimental data. Okay, I think that must be the genesis of their claim. I'm not a lawyer, I don't know, but I think that's what's going on. Okay, so when I first read this prompt, I realized that what we're being asked for, right here, sounds a lot like the estimated estimated effect of treatment in the treated, which we have been, we've already messed with a little bit here. But whereas the effect of treatment on the treated would have us condition just on X, we are now additionally conditioning on Y. Okay, we're conditioning on the outcome as well. Okay, so I'm just going to push forward and see what happens when I do exactly this. Just use the same procedure that we used with ETT. Okay, so we have the situation where they take the drug versus not take the drug. Okay, and we subtract those. And because we're in the binary case, we're going to get a lot of ones and zeros. Okay, so this first guy right here is just 1 because the counterfactual is what was observed. So what was the expectation for Y in all of this? Well, we already know it's 1. Y equals 1. Okay, and so now we need to find the expectation of this over here. Okay, and so we need the expectation of Y in 2 circumstances: one where they die, or don't die, and one where they die. Okay, and so in the case where they don't die, the expectation is the value times the probability of something. Okay, so they don't die here, right? And then they do die here. Okay, and then we carry all of this down. So now we're here on this line right here. This drops out because we're multiplying 0 by all of this. So we're just left with 1 times this, which is just this. Okay, so hopefully you see how that's working. Okay, well, this expression right here, can be written as 1 minus the opposite of that happening. So 1 minus them actually not dying. Okay, so now we have this. Well, what is this expression right here? This is the probability of necessity that we already found. Okay, so now we have 1 minus the probability of necessity. So the ones cancel out, and we're just left with the probability of necessity. Okay, so that's just interesting, but we still come out with the same expression here. But now that helps me understand maybe where probability of necessity is derived from. So that's interesting. Okay. So this is just another thing to put on the table. So we're going to go back to our expression for probability of necessity right here. But notice that we have another variable that's floating around here, z, or health status. Okay. And so it seems conceivable that as we move forward, we'll also want to keep track of z. Okay. And so we can rewrite probability of necessity like this. Okay. And then if we want to consider all health statuses, we can just marginalize over z. Okay. So we get back the initial expression, kinda, by taking our probability of necessity that includes z, and then marginalizing over z as such. Okay. So again, we're just putting this on the table because it may be useful later. Okay. So now we need to, so all of those things I feel like maybe if you sat down and thought about it, you could kind of come up with, and it may or may not be useful as we move on. But now we need to introduce something new that is not presented in the book. Roughly what's going to happen next is we're going to have to find a different language to express our probabilities in, right? Because it's really not clear it's not really clear how to represent this in something that is operational or that we can get from the data. Okay, and so we're going to introduce a new language and then translate this into our new language, and that new language will allow us to find usable expressions. Okay, so what is this new language? Okay, so what we're going to do is we're going to look at all of the possible combinations of taking the drug or not taking the drug and the outcome, dying or not dying. All right. So if we're talking about taking the drug or not taking the drug and dying or not dying, then there's 4 possibilities. Okay. So these are called A, C, N, and P. Type A is where whether or not you take the drug, Y sub 1, or don't take the drug, Y sub 0, you die both times. Okay? So this person always dies regardless of the drug. Now, if the person would not have died if they did not take the drug, but they would have died if they did take the drug, then we say that the drug caused their death, and so we call that type C. Okay? Now you have people for whom, regardless of whether they take the drug or not, they do not die. These people are called class N or type N, and they never die, or I mean, they die eventually, but not in the confines of these observations. And then you have another possibility, which is that maybe some people they don't die, or how do I want to say this? They would have died if they did not take the drug, but if they, sorry, I feel like I misspoke there. If they took the drug, they would not have died. But if they don't take the drug, they would have died. In other words, the drug is preventing their death. And so we call these guys P. Okay? Now, A, C, N, and P exist in the entire population, but we can also say that they exist in the subpopulations Z, right, for different health statuses. Okay? So for certain health, so you can imagine that these ratios would differ depending on the health status of the individuals. Okay? So again, this is just the probability, or maybe the proportion of A, of people who always die, in health class little z. Okay, and so for each health class Z, these different proportions need to add up to 100%. Okay, so I hope that makes sense. Now, if we want to know the proportion of any one of these types, and I'm just calling, I'm just generally referring to the types as capital T here, P sub capital T. Well, then we just, we just combine all of the different health classes, right? So we have PT for whatever Z over all Z's, times the probability that somebody is in health class Z. Okay, such that that when we look at the whole population, again, all proportions need to add up to 1. Okay, now here's the difficulty. We can't really know, we can't really know, if you look at somebody, you don't know if they're PA or PC or PN or PP or whatever. Now, you can give them the drug and see what happens, but you can't both give them the drug and not give them the drug. And because these different types depend on their different reactions to taking the drug or not taking the drug, but you only get one shot at it, we don't know these things. Okay, so that's the difficulty. So what we instead are going to do is we are going to try to find expressions we're going to try to find expressions that use these terms, and then select equations that create a system of equations, and then try to solve for the individual components of the system of equations. Okay, so so first we're just going to get some the formulation of a bunch of different types of probabilities that we might use here. Okay, so for instance, the joint probability of y and x, it equals this expression right here. Okay, so a joint probability can be written as conditional probabilities, and here I want to consider z, even though we just want x and y, so we're going to marginalize over z, but we get the probability of y given x and z times the probability of x given z times the probability of z, and that would be a joint probability. Okay. And so I encourage you to look at this block right here and just get the feel for how we would construct these different types of probabilities given x, y, and z, and how we can, again, use marginalization over select variables to get, just probability of y or just probability of x and y. But once you kind of get the sense of how we can build those terms, you will see how we can then take one of those, how we can build one of these expressions. We will next look at how we will insert then our proportions of these different types of individuals within a population or portion of the population. Okay, and so that's what's happening down here in this little block. Okay, so let's take, we'll just take let's do the joint probability here. Okay, but again, I encourage you to look at each of these. Okay, so we'll do one example for x equals 1 and y equals 1. Okay, so our joint probability, which we looked at right here, takes on this form right here. Okay, and so if we look just right here, right, at this term right here, the probability that y equals 1 given x equals 1 and z equals 1. Okay, well, what does that mean? Okay, well, let's try to parse this out. Okay, so when z equals z, so when z equals z, then we are looking at the types of people for whom, they are in health class Z. Okay, so we're selecting particular individuals or portions of the population with health class Z. Okay, and then who is it? What individuals die when they take the drug? Well, there's two portions of the population: the people that always die when they take the drug, that are in health class Z, and those for whom the drug causes death. Right? These are the individuals who, when they take the drug, they die. Those who would have died in either circumstance, and those who took the drug or would die because of taking the drug. Okay, so now you see how we have inserted in PA and PC into our joint expression for py equals 1 and x equals 1. Okay? And again, we can marginalize over all of z to get just the joint between x and y here. Okay? So in which case, now we're looking at the entire population rather than just health class Z, again, because we're marginalizing over Z. Okay, so you can go through and you can look at each of these types of probabilities. Check me for errors. I mean, it's very easy to make errors when when writing this. It's very easy to make errors. But anyway, so this is an example for x equals 1, y equals 1. And then I've gone through and I've just made a table here of all of the different types of probabilities, right? So we have the probability of y, of just death. So this would be, just the complete marginal probability for y. Okay, and then when x equals 0, I have the probability of y given x equals 0, and then the intervention or the conditional probability, and then the interventional probability, and then same for x equals 1. And then I have the different outcomes in the two different columns here. Y equals 0, so there is no death over here, and then y equals 1, there is death over here. Okay, and so again, I really encourage you to look at how we inserted the the types of people into the expression, and see if you can match what is given in the table. And when I say match, again, allowing for the fact that, or the possibility that I've made errors in typing this out. And if I have made errors, then please, let me know so I can correct it in the Colab sheet. Okay, all right. Now we can take, so using a similar trick to how we've, put in these types of people into these probability expressions, we can do the same thing for probability of necessity right here. And so how might we do that? So I'm going to look at this expression because it's simpler, but notice that this expression is just this more complicated expression that takes into account each health status and then marginalizing over Z. Okay, so I'm just going to go here, okay, because it's simpler to look at. Okay, but we want to know who would have. Okay, so we want to know of the people who took the drug and died here. Okay, who would not have died if they had not taken the drug? Well, I think another way that we could say that is, of the people who would have died when taking the drug, for whom did the drug cause death? Okay, so, and just by using that type of logic, you get this expression right here. It's the people who died because of the drug, or would die because of the drug. Okay, again, these are hypothetical situations. This is saying this type of person, rather than who actually took the drug and died, divided by all of those who would take the drug and die, some of which would have died anyway, and therefore the drug was not at fault. Okay, so now you see how we're folding in these different population types to the probability of necessity. So that means if we can find usable expressions for PC, PA, that we can get an expression for PN. All right, so that's interesting. So how might we do that? Well, we're going to go back to our table. We're going to go back to our table up here and look for some expressions that have PA and PC in them. Okay, and so two such expressions would be given here. Okay, you could find other expressions, but we have these ones right here, and we need to select these kind of carefully. Okay, so we need to make sure that they have at least PA and PC covered between them, and we know that we need at least two expressions because we have two unknowns, PA and PC. So we need at least two expressions, and we need those expressions to cover the range of the possible x values here. Okay, so this is what we have. All right, but notice that when we do this, so we pick our first one that has a PA and a PC, but then we have one that has a PA and a PP. So in finding a second expression, we've introduced another unknown. Okay, so you think, okay, well then that's fine. We will just simply add another expression. right here, because now we have PP, but now we've added a Pn. So now we have 4 unknowns. Okay, and so now you think, this is great, because now I just find an expression that has Pn, or another one that has Pn or whatever, where we have I pick another equation such that we have 4 equations and 4 unknowns, and we know what our 4 unknowns are. They are the different proportion types, right? So now I have 4 equations and 4 unknowns, and therefore I can just push forward, push these, through some kind of algorithm that will solve this system of equations. But unfortunately, it's not that easy. Why aren't they that easy? It's because no 3 equations are independent of one another. Okay, so this is by virtue of the fact that our outcome here is binary. Our drug is binary. We take it or we don't take it. So if we are using probability of y, or y equals 0 given do x equals 1, well, this is just 1 minus another expression here. Okay, so in other words, if we use these 2 expressions, they are not independent. They are not independent equations, right? Or whatever terms or whatever we want to say. And so by using our 4 equations, we don't actually have 4 independent equations. So that's too bad. So we can't just use 4 equations to solve the 4 unknowns. Okay. And so this leads us with the predicament of always having more unknowns than we have equations. Okay, so we're going to now find out that is why the book presents us with finding the range for the probability of necessity. It's not really explained in the book why you need that, but you need that because of this difficulty or this impossibility of solving a system of equations. Okay, so what do we do? Well, we have 2 independent equations. That's the most that we can get. Okay, and these are the 2 that we selected up here, and so let's just try to solve for some of these unknowns as best as we can. Okay, so if I take this expression, I can solve for PA, and I get this right here. Okay, and now I can kind of get an expression for PC right here. Okay, and so now I have kind of an expression for PA and for PC, and so I just plug those into my formula for the probability of necessity. Okay, and I get this right here, which is not terrible. Okay, it's not terrible, but notice that all the way through we're carrying this PP here. This is that 3rd unknown for which we don't have an expression. This is the probability that the drug prevents death. Okay. So now, because we have this guy right here, and we don't, we can't solve for it, we can at least put boundaries on it, and the boundaries on it then will imply boundaries for the probability of necessity. Okay. So we can do that in a few steps, where I'm not going to go in super depth here. One, because this video is getting very, very long, and 2, I think that just walking through the math verbally is not as good as you just sitting down and looking at it. But first we set boundaries for the probability of necessity, and we know that that's between 0 and 1. And so then we can kind of reconfigure this expression right here, trying to find a bound for PP, right? And so you can multiply this guy over to both sides, and then but ultimately you get some bounds for PP right here. Okay. Now PP itself, P sub P, is we can apply some additional constraints to it, because we know that it has to be between 0 and 1, because it itself is a proportion or a probability. And so what that looks like is this lower bound right here can take on 2 options. It can take on either 0, or it can take on this right here. Okay, right? Because this value could be negative actually, but we know that the p sub p can't be less than 0. Okay, so if this is negative, if this expression is negative, then we just say that the lower bound is 0. All right. Now, there's another constraint that we need to, implement here, and it's not straightforward because it's the constraint on Pn. Okay, but and Pn is also between 0 and 1, and because of that, because Pn equals all of this, it also applies something about P sub P, and so we need to take that into account. And this is not something that I think would be intuitive to do. Okay, so but this is kind of a little hidden step in there, and so we need to consider that. And then ultimately, what we get for the bounds of P sub P is given right here. Okay, so the minimum for P sub P is this right here, and the maximum for P sub P is given by this right here. Okay, and so now we can use these bounds to plug back into our expression for probability of necessity, right? And so again, because now PP is some range, well, now our probability of necessity is going to be some range, right? Because the PP term is fluctuating, okay? And so, so if we do that, then we get this term right here, okay? These are the bounds for the probability of necessity. Now, this is not the form given in the book. And to get the form that's given in the book, you need to do some kind of silly, that kind of algebra where you would only discover if you were playing with everything and then realize, oh, this is a cool way to express this. And so it's, it's a kind of unmotivated, silly algebra that I always find a little bit frustrating. When a book wants you to derive something that requires some algebraic trick that, it's just not intuitive. And so I detail how to get to the expression in the book, and I'm just, I'll allow you to read that for yourself. But ultimately, you get this expression right here. I think that this is where's the one that's used in the book? Yes, right here. This is what gets used in the book right here. This bottom one. Okay. But again, this expression right here, these bounds are just the same bounds that we found by ourselves, okay, with just some algebraic tricks thrown in. Okay. So that's interesting. Now, the book also talks about, the monotonicity assumption and how with that we no longer have bounds, we have an exact answer, or an exact estimate that that isn't put between a minimum and a maximum. Okay. So how do we do that? Okay, well, the way that we do that is, so far, the thing that is causing us to have these boundaries is the fact that we have this PP term here, right? So it is the assumption that for some people, taking the drug prevents them from dying. Okay, but what happens if we just thought, no, that's crazy. The drug will never prevent somebody from dying. It can only have a small to large effect on their probability of dying, right? Well, then this term right here just simply drops out. It goes away, okay? So by monotonicity, we mean that the effect of the drug on death only goes in one direction, right? It only increases or doesn't do anything to the probability of death, okay? And the way that we get that is to eliminate this PP term here. And so so this is just an assumption, right? That we can't prove this here anyway. But if we just say that the drug never prevents death, well, now we're just left with this expression right here. We're just left with the expression without the PP, and therefore without the range. Okay. So then we get that the probability of necessity looks like this, or we can alternatively express that as this, which again, involves some algebraic tricks that the book uses to get the form that's present in the book. Okay, so there you go. So now we're all the way to a usable expression for the probability of necessity. Now, the book further breaks down the probability of necessity into the excess risk ratio and confounding factor. And so in this little section right here, that's, I'm just showing how you get from the probability of necessity to the probability of necessity as expressed by excess risk ratio and confounding factor. Okay, so I think that I'll just allow you to look at that, and I'll just kind of skip it. Okay, but finally we can go all the way back and try to answer the question that was first posed in the example. Okay, namely, we need to decide from experimental and non-experimental studies whether it is more probable than not that drug X in fact caused Mr. A's death. So all that we need to do is to plug in the numbers for our expression of the probability of necessity, churn through, and we get 1. So in other words, it is, I guess, certain, almost certain, that the drug caused Mr. A's death. Okay, so that is the answer, okay, to the example. You can stop watching now. But I also want to look at the probability of sufficiency and the probability of necessity and sufficiency with these PC, PN, or the population proportion terms that we derived earlier. Okay, I'm going to gloss over most of this, but just to kind of show, I'm just going to get us to these types of expressions where we express PS or PNS in terms of these population proportions here, and then you can walk through the same steps that we already went through above, to find a final expression, or one form of a final expression here. Okay, so now we have the probability of sufficiency. Okay, so what is the probability of sufficiency? Okay, this would be those individuals who would die if they took the drug, but we only saw them not take the drug and not die. Okay, again, we could incorporate Z in here, but just for simplicity, I'm just I'm marginalizing it out, right? Just as we did for probability of necessity, right? We just marginalize it out and we get the nice clean expression here. Okay, so what would this be? Okay, well, this would be the individuals for whom the drug would cause death, right? Or so how do I want to say this? Okay, so who did not die and did not take the drug? Okay, well, the people that didn't die would be, it gets confusing trying to say these things. Who would not die having taken the drug, but would have died if they took the drug? Well, the people who would die if they took the drug, of course, are the PC people, okay, and but they did not take the drug, okay, and who else did not die for not taking the drug? Also, people who wouldn't have died anyway, okay. So we get this expression for PS, okay, and then we can churn through, and again, once again, we get boundaries. We get boundaries for PS. And then if we apply the monotonicity assumption, again, that nobody is prevented from dying by the drug, then we get, a solid expression for it. Okay. Now, finally, we want the probability of necessity and sufficiency. Okay. So this would be people for whom, if they took the drug, they would die, but if they did not take the drug, they would not die. And this is just those for whom the drug causes death. Right, that is the expression of PNS here. And so once again, we can find boundaries for PNS, and if we apply the monotonicity assumption on PP, then we get this expression right here. Or if we would have started with do expressions instead, then we would get a different expression, and so on and so forth. But this would be one acceptable expression for PNS. Okay, we will call that good and then get into question 4.5.1 in the next video.